Say something from back there, Chris. Say, introduce yourself.
Hey, Caleb. I'm Chris Lindsay, one of the three in the cross country adventure class.
Hello,
Did you hear
Chris.
that?
Yeah.
Yeah. So speak a bit louder if you say so. All right. And Caleb's also the guy who created the XE Nav app.
Thank you.
That we've been
Yeah.
using.
That was awesome. Yeah.
Thank you for
I haven't
playtesting.
That was awesome.
Okay, over to you, Caleb.
Dude, fine.
Wait, who else is in the class?
Brian, I'm in the XC class as well.
This is new one. And again.
So there's Ryan. Can you see Ryan?
I couldn't quite hear you way in the back, actually.
My name's Ryan. I'm in the XC class as well.
What's up, Ryan?
Chris. Oh, I'm Will.
Will?
Around.
And then the rest are just a bunch of people where we picked up at Johnson Landing.
Nice. All right. Hello, everybody. I'm Caleb.
Hi, Caleb.
Hi, Caleb.
Thank you. All right. Let me present my screen here. All right. Is that working?
Yeah.
Yep.
Great. All right. Today I'm going to talk about weather as it pertains to cross-country flying slash fly camping. I'm going to have kind of three sections to this. The first one, I'm going to just kind of cover some fundamental basics of weather, meteorology, kind of like how everything works. The second, camping and what to consider when picking your camping spots. And then the last one is just probably the longest section, and that'll be just flying across the countryside, like all the stuff you need to think about when you're picking your routes for big long trips. I'm just gonna sort of steamroll through this, so interrupt me if you have a question. I'm more than happy to just like go down a rabbit trail or answer questions. So just speak up in case I can't hear you. Alright. Fundamentals. First I'd like to say you should go buy this book called Understanding the Sky. I didn't write it, so it's not like I'm getting a cut from this, but it's the best book I've found that has it explains weather for an ultralight pilot. So it's like all the things that you need to know to be able to look out at the sky around you and understand like what's happening. It's an amazing book. It's not that hard to read. I loved it. I thought it was awesome. So you should go read it. Everything I'm going to be talking about is in that book in much better detail and like better explanations. All right. The first concept I want to talk about is called lapse rate, and this is like the root of everything. All it is the principle that air gets colder as it goes up in the atmosphere. If you go to like a weather model, you can see this effect by looking at what's called a sounding. This is windy.com, and I have enabled a little plugin. It's available on the free version. Anybody can do this, where I can see on the left here what's called a sounding anywhere I click. What this is like a side view of the atmosphere. It's like a cross section, and it's like a graph. Is this too detailed? Should I zoom in or anything?
It's good enough. Remind me, y'all, at the end of this, I have a great YouTube series on how to understand these graphs if you really want to know.
Great, nice.
Yeah.
Hey, Caleb. Really quick, can you record this session?
He is.
Yes, it's
You are?
recording right now.
Awesome. Thanks.
Yeah, who said they had a stuff on these graphs?
Oklahoma University put out a 5 or 6 hour lecture series from a college about how to read these graphs and understand what they mean.
Nice. So
It's You can muscle through all like 6 or 9 hours of it. It's really good stuff, man.
Have you watched it all?
Yeah.
Nice. All right, so you should be able
Texas,
to.
like Tornado Alley, so I know a lot about those graphs.
Oh. Nice. I'm sure you've seen some crazy soundings then. All right. Well, for everybody else, this is the sounding. It looks kind of crazy and it's a little wonky, but I'm gonna break it down really quick. Speed run. I'm sure you've all heard of an XY chart where you have like values, right? And you can like plot data on this graph. All this chart is like a funky version of this. You still have this axis, but the other one is like slanted. It's called a skew T chart. So it's a little bit weird, but basically know that it's just a graph. And what we are graphing is the temperature of the air as we go up in the atmosphere. So this red line, I should pick somewhere else so it's easier to see. There we go. Okay, so this red line is the temperature as you go up in the atmosphere. On the bottom you can see the numbers. If I hover my mouse, it'll kind of show me the numbers as I go up. It shows me the temperature in the red right here. And on the left side you can see the altitude, 3,000, 6,000, 12,000, etc. Alright, so coming back, lapse rate. A lapse rate is the rate that the air should be cooling down as you go up in the atmosphere. If there was no weather, like nothing weird was going on at all, the temperature should cool down at this rate right here. This is called, oops, it like squiggled there. This is called a dry adiabat. I don't know if this will come through. It's a really tiny line in the chart, this little green line. Can you see that, or is it like getting crushed?
Yeah.
Okay, there's a little green line. That's called a dry adiabat. If you were like in the dry desert and you took a bunch of air in like a balloon and you pushed it up in the atmosphere, it would cool off this fast. So at ground, let's say it's 50 degrees, you go up and up, eventually you at, let's see, that's like 13,000 feet, it's minus 20. It's just like a standard curve. However, in real life, that just doesn't really ever happen. Instead, you get this squiggly line here that the weather models are showing you. So that was dry air. If the air is warmer than the air around it, then it wants to float. You all heard like, warm air rises. So if you had a pocket of air on the ground right here and you warmed it up over the oven to this temperature, it would want to rise because as it goes up, it's still warmer than the air around it because this is the temperature of the air around it. And it would just keep rising and rising until it came back to this curve. The sun heats the ground and has the same effect. Sometimes this chart during the day, here's an example. During the day, this graph is showing you how the sun heats the ground right here with this green line. Sun heats the ground, warms it up, and it like bubbles up like this until it comes back and touches the line. In layman's terms, this is kind of what's happening. Alright, so if the line is the red line, if you open this up, you're looking at the weather, if the red line is really slanted to the left like this, then it's easier for this warm air to rise, and it'll rise much higher and much faster, because as it goes up, it's running into colder and colder air. The air is turning colder faster than it should be. This is really unstable conditions. It means that any sort of disturbance on the ground that starts kicking up air will make that air sort of like drip and like pop and like shoot upwards like a thermal. Actually, exactly like a thermal. This is unstable conditions. If you open up this chart and you see a very vertical line, these are very stable conditions. This means that you would have to heat the air really hot to make it rise before it found air that was the same temperature as it and stopped rising. Any questions? Am I going too fast?
Nope.
Alright. If you're near the ocean, you may actually see this graph reverse direction and go like this. And you'll see like this little nose stick out. This is an inversion. This means that there's really cold air on the ground, and if you take off and you start flying up, you suddenly encounter very warm, nice air. The inversion means that nothing is going to be rising above it, because you'd have to heat the temperature of the air on the ground, like in this case what I just drew, you'd have to heat it like 40 degrees before you could get it warm enough to punch through that inversion layer and still be warm enough to keep climbing after it got through that. So this is like extra stable conditions, and that's why beach flying is often really nice. It's because cold air from the ocean blows in underneath all the warm air and creates this inversion, holds down all the thermals. Alright, any questions? That make sense?
Yep.
Cool. Alright, so let's bring in humidity into the picture, and that is this blue line here. When the blue line comes right up and touches the red line, that means that the air is fully saturated with water, and you start to get cloud. Let me go somewhere where it's more obvious that you're going to get clouds. Alright, this will have
Down
to do.
here, there's cloud.
Yeah, right now there's clouds.
Oh, yeah? Alright, let's go to right now.
Well, it's Salton Sea right now. Wendy's also not been great today, so.
Well, this will still kind of show it. Alright, so this is actually showing that you're going to have scattered clouds. You can see it right here, this gray patch. It's showing you that you're going to have clouds. So, I don't want to get too far into the weeds, but this plot will actually kind of show you that there's clouds there based on what these curves are doing. But anyway, if the blue line meets the red line, then you're going to get rain, essentially, or really dense cloud. Let's see, what else do I want to say about that? I talked about the dry adiabat. That is the temperature the air should cool off normally, this curve. But if the air is wet, if it's like cloud, then it doesn't cool off at the same rate as you pull it up in the atmosphere. It actually cools off slower. And it cools off at this speed right here, this dashed line that is sloping to the left. And that's what makes this graph like so hard to read. It's like all these crossing lines, but you get used to it. Alright, so the reason air cools off slower when it's wet is because colder air does not hold as much water. So as you cool off the air, it can't hold all the water it's holding, and it will start to condense out of it. Rain, essentially. And it's kind of a continuous slow process. It's like wringing out a rag. If you took that parcel of wet air and you start moving up, it will slowly squeeze out all the water. There's a chemistry thing that makes it so that when that water condenses out of it, it releases what's called latent heat, and it actually warms up that parcel of air. Hence why, as you squeeze out the water, it stays warmer as you go up than it would if it were dry. This is really important because this is what makes clouds and thunderstorms and all kinds of crazy stuff. So to explain this again, if I have dry air, this might be mostly stable because this curve is steeper than it should be. This would be the natural curve right here. It's steeper, so it means that like even if I push the air up, it's just gonna hang there or come back down. But if it was wet, its natural curve is over here, and it's going to spring up higher and float up higher. So warm air rises. When you condense the air and it releases more of its own heat, it becomes even warmer and rises faster. That's why when a cloud starts to form, it will suddenly form faster and start to billow up. That's why clouds sort of billow the way they do. In extreme situations, you get thunderstorms where the cloud pulls in more air, which condenses off more water, which produces more warmth, which like heats up the cloud and makes it rise faster and bigger. And this is what's called a cloud engine. And that's how a thunderstorm gets so big. It's like poking a hole in a water balloon or something, and the water starts ripping the hole bigger and bigger, and it like feeds its own process. That's a cloud engine. Anyway, this chart helps you see when that could happen. It helps show you when thermals are likely, or when thermals are super unlikely. This is like the go-to chart when you're trying to understand what is happening with all the weather around you and like what the air is going to be like when you go up and go fly. Quick note, the other little part of this chart on the right side, this part here, this is showing wind speed as you go up. Right now it's not very interesting, it's just like 20 miles per hour all the way up. Eventually gets faster, but if you see, I'm just going to go somewhere where we can see something interesting.
Pick Colorado.
What was that?
I said pick Colorado.
Colorado. Okay. Actually, I want to show somewhere that has a mixing inversion. Here we go. Here's an example. This happens to be down towards the bottom of the storm we're all experiencing. So we can see a gradient of wind speed here, where it's slow on the ground and very quickly becomes really high speed. Something to be watching for at this chart is correlating changes in wind speed to changes in temperature. If I saw a temperature that looked like this and a wind speed that looked like, let's say, this tells me that there's an inversion layer because there's cold air on the ground. It's colder than it should be. There's warm air up top. So there's not going to be any thermals. But the wind speed is dramatically higher up top than it is on the ground. So there's going to be a shear layer in here somewhere, because warm and cold air don't like to mix, and you have fast-moving warm air on top, and you have slow-moving cold air on the bottom. So this graph will almost always show you like a smooth line. It's not like that in real life. Sometimes it'll actually be like this. Clear this so it's easier to see. Sometimes it'll actually be like really stark, or maybe it's like a couple steps. It can do all kinds of stuff, like the real actual data. Anyway, that's how you can spot shear layers.
Why would we want to see shear layers?
A shear layer is like a really quick transition between wind speeds as you go up or down. Well, I guess they can happen left or right too, but anyway. If you're flying along and you go into air that's a totally different speed from you, then weird stuff can happen, because it's like as if you're suddenly flying much faster or much slower. And that can be really bad if it's coming from the side. So it's almost like you're suddenly flying 20 miles per hour sliding to the right. Imagine that does like really weird things to your wing. Your wing will like shoot off to one side of you and stuff. It's not a great time. So looking ahead on your route when you're flying cross country and seeing like, oh, there's a shear layer up ahead. You can make a judgment call of like, ooh, this is a nasty shear. I expect this nasty shear in here. I don't want to go there. Or you can be like, there's a shear here, and I'm going to fly through it. I know it's here, so I'm going to fly this direction through it. And so you can know what's out there. Alright, I'll keep moving unless anybody wants to talk more about shear layers.
Just a real quick question. Are those arrows on that right portion of the wind speed graph, are those the wind direction?
Yes, it's a north up, so it's like this, north, south. The arrows, the only thing really to look at for the arrows is to see if they suddenly switch directions. Like, the chart could actually look like a straight line, but then if the arrows are doing this, and then they suddenly go the other way, they might not always show the drop in speed right in the middle. They'll just show it like continuous, like in this case 20 miles per hour all the way up, but the arrows are pointing completely opposite directions. That's like one crazy shear layer. So the only thing really to look at for the arrows is if they dramatically shift directions. In windy, if you really want to know the direction of the wind, just pull up the the wind layer and scrub through the altitudes and get the direction that way. It's a little bit easier, I think, to read.
I just want to say something. Did you guys, anyone see on YouTube the video about a year ago of a guy flying along in very calm air, and his wings suddenly went like that, and he shot to the ground, and he was hospitalized. That was a shear layer. So he went up, and it was calm, and he did the forecasting, and that's exactly what happened. He hit a shear layer, and his wings just literally just crumpled, and he just went straight. So that's what it was.
We hit some shear on our flight back this morning.
Yeah, we did. So the two
They're pretty
things to
low.
keep an eye out for then are change in speed and change in direction. Rapid change.
Direction predominant. You do not want to change in direction, especially a sharp one.
Is somebody still talking? I can't quite hear.
No, we're all done. Back to
Okay,
you.
sorry. I can give you my advice for how I like to fly through shear layers. If is anybody interested in that?
Yes.
Okay. Let's just pull up a cross-sectional view, so we're not like looking at a white screen all the time. Okay. Let's say I know that on the ground there's air blowing this way, and up top there's air blowing this way. It could be that like a shear layer can still happen if the air on one side is not moving and the air on the other side is moving, but just for a dramatic effect, the air is moving quickly in both directions. If I fly, let's say I'm flying along right in the middle, right here, and I'm headed this way. I'm flying with the wind on the bottom. Actually, you know what, let's go back. Let's say I'm down low, I'm flying this way. I'm flying downwind. If I start climbing, I will suddenly hit a much stronger headwind, right? Because now I'm facing into a strong wind when I was going downwind. So it's almost like I'm flying super fast. I'll suddenly gain a ton of lift and get sucked up into the layer above. That's my preferred situation if I'm climbing through a shear. I like to be facing into the wind that's up top. If you are facing the opposite way, so if I was flying into the wind, which we often are, right? Flying into the wind, and I start climbing, what'll happen when you start touching the layer that's at the top, it's like you're suddenly getting sapped of speed, right? Because suddenly the air is moving with you instead of moving past you, right? Like it's almost like you're losing speed for some reason. And it will get really hard to climb. Even if you're at full throttle, sometimes you can just sort of skim along right here, because it's like you're taking off again, like you're launching from the ground, right? You're on the ground, you're going from 0 to 30, let's say the bottom is 15 miles per hour and the top is 15 miles per hour. Well, no, that's too fast. Say 10 and 10. That's a difference of 20 miles per hour, right? So as you climb, if you're facing this way and as you climb, it's like you just lost 20 miles per hour in your speed. And it's like you'd have to give it all the beans to catch up again and keep going. But the whole time you're like trying to take off again, right here, you're right in between the shear layer where all the turbulence is, because, you know, these layers are mixing right here and creating turbulent layers possibly. And you can actually like skip, like bounce into this air and come back down, and bounce up again and come back down. And your climb basically looks like this. It's not really fun, right? And it feels like it takes forever to get up into that top layer. So I advise pointing into the wind if you're climbing.
David, I have a question. When you're talking about speeds, you're talking about airspeed, not ground speed, yeah?
Correct. Airspeed. Airspeed is what matters. If I was if I'm up here and I want to go down, this one I think is a little less clear. I think like the example I just gave, it's pretty clear like what you would want to do, because you just quickly go through the layer and you have more wind speed, so it's not like your wing's going to collapse or anything. It's a little bit more subject to opinion, I think, when you're coming back down, because you could have the same mentality where if I'm up high and I start sinking down into effectively the tailwind, I'll sink really quickly and I'll get through the turbulence faster, right, if this is a turbulent layer. But there's also reasons you might not want to do that, because if it's super dramatic, you could take a collapse, because it's like the wing needs wind coming in the front, right, to fill up the cells, and if you suddenly get a tailwind, the wing will shoot really far as you're like diving to gain speed again. So you might take a collapse if you were like on a really slippery wing or something. I don't know. Like, I think it would take a pretty dramatic shear to do that, but you know, that's your judgment call as a pilot. It's not so bad doing it the other way when you're coming down. So if I'm coming down, I'll usually fly downwind, because you can sink a lot faster than you can climb, and it doesn't cost any throttle. So even though as you go down you'll hit the headwind and you might bounce a little bit, or you know, slow down as you transition, it'll be a lot safer, and it's not like you have to be pegged full throttle to do it, because you're just like hitting a headwind. So that's my preference. Usually that's what I'll do, but I think that one's more subject to opinion. But pretty much just like in any situation, you don't want to be crosswind when you're going through a shear layer. Alright, does that make sense?
Yep.
Yeah.
Alright, so I talked about air stability and lapse rate, cloud engine, pressure zones. Right, so I think when you're flying around, day flying around some area, you don't really pay that much, at least I don't really pay that much attention to like the big picture, like what's going on like half a state away. But when you're flying cross country, especially if you're doing multi-day runs, you can't really afford to just ignore the bigger picture of what's going on. So I'm going to kind of talk through sort of the bigger components of what's happening, and I'm just going to glaze over this as like a big topic, right? This is macrometeorology. People have like full-time careers to interpret this stuff and give you like you pull up the weather channel, it's like local on the 8s, right? And they like show the weather fronts of like low pressure zones and high pressure zones. That's exactly what I'm going to talk about. Alright. Oops, I think I zoomed out too far. Alright, this is still just windy.com, but I've turned on pressure. Down here in the bottom right, there's a little switch, just says pressure. This is showing me almost like areas of a map that show you the elevation of hills. It's kind of just like that. These white lines. I hope these are coming through the compression.
Yep.
Okay, great. So these lines, you can kind of just think of them as like slopes on a map, right? Only in this case, instead of graphing elevation, we're graphing air pressure. You have high air pressure zones, like this H right here, and you have low pressure zones over here. Right here. Low pressure zones tend to bring storms, like the big ass thing that just came down the coast. This was a huge low pressure zone. If I back it up a little ways, it becomes a little more obvious. It's not really loading, but low pressure zones bring storms, and they often bring cold wind as well. But most importantly, they bring unstable conditions. Well, sort of. I take that back. Take that back. They bring cold wind. High pressure zones are stable conditions. A low pressure zone is kind of like the whole area being more buoyant and trying to float up. If a thermal is like a warm bubble that's trying to float up, a low pressure zone is just like a gigantic version of that, like on a big macro scale, because the atmosphere is pretty thick, sorta, and what we know of the atmosphere, like what we experience, is just like the bottom sliver of it, and there's all sorts of stuff that's happening above our heads, like all these huge movements of air, like piling on top of each other or like swirling around, all driven by the Coriolis effect, where the sun is heating the middle of the Earth more, and the Earth is spinning, and like weird physics stuff happens. The Coriolis effect. If you want to understand that, you'll have to go look at another video. I don't have time for that. But basically, the atmosphere be crazy, and it's like swirling all over the place, and it tends to pile up in bunches, and those piles of air are called high pressure zones, where the air is like kind of thicker and piled up more, and it's pressing down. So low pressure zones are heaving upwards, they're expanding, they're like floaty and buoyant, and high pressure zones are crushing down. If we go back to our sounding chart, what this means is that a high pressure zone will push all the air down, which warms it up and generally tends to create a more vertical temperature line, which is stable conditions. A low pressure zone is almost like, and again this is just sort of layman's terms, almost more like a memory tool. A low pressure zone, if it's all buoyant, it's almost like some of the air on the ground gets a free ride to like get a little higher than it normally would have been, and you get more, there's a higher probability of thermals and bubbly, unstable air, essentially, because the curve has gotten more shallow, like this. Alright, so let's see, where should we go next? Any questions? I didn't hear any. Alright. I hope I'm not like losing everybody. It's just like nerding out over, you know, all this weather stuff.
Everyone seems pretty intently focused on this side.
So I should speed up?
No.
No, like we're all focused and like absorbing, so it's good.
Great. Alright. Okay. Let's see. Low pressure zone. This is a low pressure right here. This is a low pressure zone. Again, Coriolis effect. The wind tends to go counterclockwise around a low pressure zone. And you can remember this because L for low, L for left. Low pressure, left turns. And an interesting thing about this spin, you find a better example. Actually, this one is a really good example. It's a crazy low pressure off Alaska. low pressure zones bring cold gust fronts, or cold fronts, as we call them, right? I'm showing temperature in this graph right here. The wind is sweeping around to the right. It's doing a left turn. It's 51 degrees on the right side. It's 37 degrees on the other side. It's a pretty dramatic shift, but you know, this is also like 200 miles apart. Or more. Anyway, they bring a cold front of air. Cold air is more dense than warm air, and it tends to slide underneath the warm air. So let's go to the California coast. Let's go to the Fly Halo. Where am I? A bit too far. Nope, there it is. Okay. So, the land is warming up and creates a big warm area. It's warming up from the sun. That cold front comes down the coast, and it's got this freezing cold marine layer, and it will push underneath the warm air until it looks like this. Like so. And right here is your inversion layer. So inversion layers tend to be more common during near the coast, where you can get this marine layer washing in, and it as it pushes in, it's like a wedge pushing this warm air up, and this warm air is from the land, so it tends to hold water from like trees and stuff. As it goes up, it cools off enough to start squeezing out the water and form clouds. Hence why when a cold front comes down the coast, you tend to get a bunch of rain, because it's like a giant wedge pushing up all this warm air off of the ocean like a big scoop, lifting it up, squeezing out all the water. Later I can talk about all sorts of weird ways these two fronts can interact on the coast. If any of you do any coastal flying, I think we should do that, but I'm going to keep moving. Alright, any questions about that? I'm going to move on to the next section, if not.
Teams, get over here.
Great. Alright, so that was sort of the fundamentals of like the narrow picture, how to interpret like the stability of air, big picture, how to kind of visualize what's happening, like what kind of weather's blowing in and what it's going to bring to you. Alright, next topic, camping spots and what sort of weather things to consider when you're picking camping spots for fly camping and such. First one is mountain peaks. Any of you ever landed on top of a mountain before?
Yep.
Yup. Okay. Mountains tend to divide the air. Like you can have one of these fronts can be blowing in on one side, and on the other side you can have like a totally different weather system happening. And as one of them builds up and gets bigger, it can start spilling over the top, causing like no wind down here and super high winds across the top of the mountain. As wind hits a mountain, it gets redirected up and slides over the top. It sort of compresses right here like this and goes really fast over the top. This is called Venturi. So if you're camping on a mountaintop, you should know that even if the wind's aloft, say something like 5 or 10 miles per hour, you may experience twice that. if you're camping on the top of a big mountain like this that has a bunch of air moving on one side. Let's see. That is Venturi. Venturi is also sort of a general term where the air speeds up when it goes through a narrow gap. So you can also get Venturi from like, you probably are more familiar with the term from, you have like a saddle between two peaks. The air will go faster through the gap because it's like trying to avoid having to climb over the peaks. So I guess you can take away from that is if you're camping in the middle of a saddle, you may experience a lot of wind coming through the gap. Alright, let's see. What else did I have my notes on? Mountaintops. Venturi. Convergence during the day. You may experience totally different wind in the evening versus the morning on mountaintops because during the day the wind tends to, let's say the sun is on this side heating this side of the mountain and you've got like sort of a gentle breeze, like the that front is blowing in, it's kind of pushing on this side of the mountain. The wind will actually go up on this side of the mountain and up on this side of the mountain and create a convergence where they meet right in the middle, and it's just climb for days right at the top. So things could get kind of bumpy and weird if you're landing on a mountaintop in the middle of the day, if there's like wind approaching one side and sun shining on the other. So that's an effect to keep in mind as well. These are all sort of like miscellaneous things to look for. I guess basically what I want to communicate is you need to kind of like understand all the different situations that can happen and kind of like what the factors are at play so that when you get to the mountain and you want to land, you can read the situation and make your own predictions for what's going on. And then when you start getting into the air and you start feeling something that matches your predictions, be like, okay, I'm probably right. And you get a little closer and it still matches your predictions. You know, you can have good confidence that you know what you're getting into. Or if it totally doesn't match your expectations, you know that like something different might be going on and you need to reevaluate the situation. Let's see, anything else I should say about if you're camping on a mountaintop and you're going to launch the next morning, make sure that you check the wind on both sides of the crest so that you don't get fooled by rotor. So that wind, when it gets to the top of the hill and is redirected, or hits the mountain and is redirected, if it's strong enough, it, instead of sinking right back down on the other side of the mountain, it will peel away and just shoot off the top of it, right? And on the back side of it, that means you get like this swirling rotor going on, like so. And if you're standing right at the top, right here, you may feel wind coming at you on both sides of the mountain. And you're like, oh, this is great, convergence. It'll be like a nice lifty way out of here. And I can launch either direction I want. But in this case, that would not be true. If you launched this way, you're going to go right into rotor, and like, you know, it's probably not going to be very fun. If it's really bad rotor, it really might not be fun. So you want to go down a little bit, walk a little bit on each side of the crest to see which side is stronger, has the stronger air, and that'll tell you what the dominant wind up top is doing. And then my preference would be to launch into that dominant wind, because the air is going to be a lot smoother on this side of the mountain. Alright, I think there was something else I was going to say about this. I don't remember. Okay. Valleys. Should I go into my examples first? Yeah, I'll just keep going. Camping in valleys. Most of the effects you will experience in a valley kind of has all the same. It's the same thing. It has different names, different situations. Katabatic flow, or drainage, or Bora winds. So they're also sometimes called. If you were camping, this is Owens Valley, famous for these massive mountains on the sides. If you're camping right here, when the sun comes up in the morning, it's on this side. This area over here will get warmed up and starts to try to be more buoyant, but this side of the mountain is going to be in shade for like a couple hours, and it is cold. At night, when the sun is not shining on something, that thing will actually slowly radiate heat away in the infrared spectrum and will get colder than the air around it. This is why you can actually get frost on, say, grass when the temperature didn't get below freezing at night, because the ground is actually glowing in the infrared spectrum and it's emitting that energy away in the infrared. So it's trying to cool down. This is why if you just shoot something out into space, it will get really cold really fast, because it just radiates all the heat away. Anyway, the side of the mountain is doing the same thing. It's radiating that heat off into space all night, and it gets super cold. Super cold air is very dense and will try to sink, and it will flow down the mountain. This is katabatic flow. This hill, or this mountain in the morning, is so big, I would not be surprised if you experience something like 15 miles per hour in the morning in the right conditions. But it's just along the surface of the mountain. It's maybe like less than 50 feet thick, and it's gonna wash out to about here, and it's just gonna dissipate as it hits all the stagnant air over here. It's a very localized effect. It'll just keep flowing down as long as it's downhill and cool. But it can be pretty windy. So, when you're picking your camping spot, think about what that spot is going to do in the morning when you go to take off. I have some examples of this. Lake Powell. Actually, I'm going to do Mono Lake first. So I just talked about katabatic flow. So I once camped here. This is Mono Lake. On the right, it's 6,300 feet, and up on the left, it's about 7,000 feet. So,
Hey, Caleb.
Caleb, just so you know, we got about 60 seconds lag before we see your images that you talk about.
oh, okay. I hope that wasn't really confusing then.
It's been pretty good until right now. Now we just hit Mono Lake.
Oh, just now?
Yeah.
Geez, you guys are slow. Okay, to recap, 7,000 feet up here, 63 down here. I once camped, it was like, I don't know, right here. It didn't seem like that much of a crazy slope, but in the morning we were experiencing, I think it was like 12-ish miles per hour. I don't know, Matt, you probably remember. It's something like 12 miles per hour every morning for like 2 or 3 mornings in a row. And it was only about 30 feet thick and is flowing downhill. As soon as the sun came out, it dissipated and it stopped. But that gives you kind of an idea. I mean, this is a really big area up top. Like this big area up here cooling off is really big. And this body of water will tend to sort of retain some of the warmth. So in the morning, this is still trying to be a little bit lifty. So that can kind of suck in the air a little bit. But anyway, we experienced quite a bit of downhill wind in the morning. I totally did not see that coming. It definitely affected the way I see picking your camping spots in the morning and being careful about camping on these kinds of slopes. if I was going to camp on a slope, I would want to do it either where I knew that the wind, the predominant wind of the next front during the next day was going to be going upslope, so I just wait for the daily winds, or I would do it up against a sun slope, the sunny side of the mountain. So in the morning, this hill warms up, pulls the air up, and you have the opposite of the katabatic flow, and then you can launch downhill into the wind. So, pretty big difference, you know, just picking your camping spot. Launching uphill into the wind or launching downhill into the wind. Alright, so that was Mono Lake example. Let's see. Lake Powell. You zoom over to another spot.
Yeah, Caleb, is there any way of it's now getting worse? Is there a way of, I don't know, restarting something for you at your end, or?
It's probably not me. I'm on a gigabit connection.
Yeah, maybe let's reset your screen share real quick, and maybe that'll kind of catch us back up.
All right, stand by.
So is that something I do? Is that what I? Oh no, you've done it.
I did it.
Because your face and your mouse cursor are both real time, but then the screen share is what's behind.
Oh, really?
Yeah.
Oh. It's weird.
Yeah. So we'll see if this fixes it.
Can you see Lake Powell?
We got Caleb Johnson has started screen recording or screen sharing. Black screen.
Black screen.
Give it
Go black.
30 seconds.
Oh, maybe I should stop recording.
Nobody wants the recording
Oh,
though.
the recording.
There it is.
Yeah, now it's appeared now.
Good.
Oh, it
Yeah,
gave me a little
mine-
pop-up. Participants can now see your screen. All right, can you see Lake Powell?
Yeah.
Yeah.
Great. All right. Here's another example. This one's from the Wingman trip. One night, Ryan, Joe, and I camped right here, but the water was like 30 feet lower than it is in this picture, so this was actually a really nice sandbar. There were almost no winds aloft, so I wasn't worried about anything swirling into these huge canyons. What I was thinking about was, on the right, we have like this big fan bowl thing that funnels into this canyon. And on the left, we have the body of water, which is almost like a big capacitor. It's just sort of like trying to keep the same temperature all the time. Big body of water. Although in the daytime it's usually colder. When we landed in the evening, the sun is off on the left and it's heating up this huge fan, which is, you know, making it warm and floating upward, which is sucking air off the water up the canyon, which is awesome because we landed into like a nice 5-mile-per-hour wind that was going directly in line with the canyon. In the morning, it is the opposite effect, where the water sort of retained some of its heat in comparison to everything else, and at night this got really cold because there's no trees or up there or anything. It just radiated all its heat away at night. It gets dense and it starts to sink down and flow back towards the water, and so in the morning we launched up the canyon this way, and we launched into like a 5-mile-per-hour wind. So it was like the opposite story, evening versus the morning. I knew this would, well, I didn't know, but I figured this would be the case. So the spot that I chose to camp was very level, I knew that we could launch in either direction. A bad idea would be to camp right here. Is the screen caught up? Can you see that?
Yeah, it's
Yep.
way better.
So a bad idea would be to camp right here because you kind of just have one option to launch, which is this way. Because launching this way, you go right into the box canyon. And, like, maybe you're a badass pilot and you can, like, pull it off, right? But, like, maybe you don't want to do something crazy when you're carrying, like, a ton of camping gear and, you know, you're off in the middle of, like, nowhere. So, I don't know. That's your decision, I guess. But I wouldn't want to launch, like, straight into the box canyon. So, yeah, again, just, like, thinking about what is this going to be doing in the morning versus the evening. In the evening, you may come down the canyon this way, and you're like, oh, this is great. Just, like, land right into a little headwind and touch down in the sand. Like, this is awesome. And then in the morning, the air is blowing cold down the canyon. And then you have to make a decision, do I launch downwind over the water, or do I, you know, try my luck and launch straight into the box canyon and just, like, hook it really sharp as soon as I get in the air? Hope that I can, right? And just, like, slam into the side. Anyway, things to think about. Weather things. Here's a... Now let's do Tori next. I'm gonna zoom on the map again. Hopefully you guys can keep up. Alright. Are we looking at Tori?
Yeah.
Great. Okay, so this was one of the stops on the Wingman trip. We camped essentially right here. And the mountains are shaped like this. And it's created a giant bowl. This whole area right here. The whole watershed in this whole area goes right down through this gap. So at night, all of this cooled off, got really dense, and in the morning, it is howling through this gap. And this would be the Venturi effect, right? Where you have a ton of air trying to get through a small gap and it's squeezing through at high speed. And in this case, it's flowing downhill. So most of us could not launch into this really high wind. We had to wait it out until the sun was well up into the sky, heats up this area so that it stops trying to sink, gets a little bit warmer, and then this flow stops. And then it stopped actually pretty quickly. As soon as it started tapering off, it was like 30 minutes, and then it was like no wind at all. And then we were literally launching forwards again. It went from like 20 miles per hour to forwards as soon as that flow stopped. Yeah, so I guess, again, another thing to think about when you're picking your camping spots. What you might expect in the morning, even though the winds aloft didn't look that crazy. Like, it was like, I don't know, something like 10 miles per hour aloft going in this direction, but it was so much higher than we expected because of this effect. That whole bowl drains through that gap. So if I was fly camping and I knew I had to camp somewhere in here, I would try to stay out of that flow. So the flow is fastest right in the middle down the channel. And it's usually not so bad right here and basically wherever the mouth starts to widen. Good. Well, it's like this. and bad. Maybe where we stopped.
Thanks, Canyon.
Thanks, Kenny. Anyway, all right. Next example. This one's a lot more boring. I'll just skip that one. It's not that interesting. All right. Next section. Unless anybody had any questions about camping spots and weather.
Yeah, I had one on the katabatic. Is it strong enough to create a shear? Sometimes.
Yes, it can totally create a shear. However, katabatic flow is usually pretty thin, and so if it's creating shear, it's like losing a lot of energy while it does that. So it's not common to have like a big shear from it, but it totally can. Totally. No other questions?
No, all good.
All right. Next section. Traveling, traversing, cross country, and planning your routes wisely. So we talked about on the macro level, you have the fronts moving around. You have the pressure zones creating stable and unstable areas. We talked about shear layers and how to fly up and down through them. We talked about what causes thermic and unstable conditions. We talked a little bit about clouds. Didn't really talk about storms that much, but you know, pretty much when we see storms, we just don't really fly. Anything in here? Does anybody want to drill down into any of these sections more? Nope. Okay. On a micro level, we talked about lee side rotor on mountains a little bit. Big sink over water. Alright, so big water crossings. If you're flying over, let's say, the Salt Lake, this body of water is big enough to create its own high pressure zone where it is cool during the day and it's like it's shriveling up that water, shriveling up that air because it's cool and it's shrinking. It's compressing as it's cooling down. It shrinks that that air, makes it cool, but the sun is heating up everything around it and trying to make that float up. And so you get lake effect, where the air is moving down over the water and out at the shoreline, like so. So if you're crossing really big bodies of water, you may experience sink over top of it, enough to affect your fuel economy, possibly enough to even notice that you have to run like a lot more throttle to stay aloft. Kind of depends what the conditions are, but it can be dramatic at times how much sink you can get over water. If it's super sunny, then the air over the land is rising a lot faster. That exacerbates the effect and makes it way more powerful. So yeah, crossing big bodies of water, pack some extra fuel. It will be really smooth air generally because there's no thermals. And you're not like getting any rotor from anything. It's just air being pulled down from the upper atmosphere. So that's great, but you know, it's not like you get a great glide ratio. Yeah, this is lake effect. Same thing happens at Salton. Why you can fly there pretty much all day, because Sultan, I think the effect is actually a bit weaker because it's so shallow. The water actually warms up considerably. But anyway, cold, blowing out. Sun heats the land, goes back up. And this is why you'll start to feel the turbulence. Well, if it's really sunny, you start to feel the bubbles here. And you'll really be away from the lake effect by the time you reach here. Alright, flying down valleys. So, if you're flying in the mountains, let me find a valley. Let's go back to Owens Valley. Alright. Are we caught up? Should be looking at Owens Valley.
There it is.
Alright, so if you're flying down a valley in midday or, you know, any time when the sun is up anywhere reasonably high, the sun is heating up this mountainside, not the other, like we talked about, and this creates a circulation pattern that happens in pretty much every valley, where you have warm air going up this side, cold air going down this side. In the middle, weird stuff can happen. Usually what happens is you get what they call like down valley or like valley winds. Something that free fire pilots will talk about a lot, like if you're watching them fly like in Switzerland or something, where they're up at the mountain peaks like doing their soaring thing, and then they bomb out, and as soon as they punch down into the valley wind, it's like, oh, it's all windy now, and like, oh, this stinks, right? It's like they get sucked down into this lower effect. You probably won't really find that super strong in Owens Valley, but, you know, just for example here. Valley effect is this area here that is actually blowing up or down the valley. Let's say it's blowing down the valley this way. So if you fly right here, you're going to get free lift, and you're going to get thermals. And that's where you'll find all the free fire pilots flying on this side of the valley during, you know, the first half of the day. You fly on this side, you're going to get sink, possibly dramatic sink. If you fly right down the center, this is where you'll find, I hesitate to say this, you may find calm winds in the center of the valley if this valley wind is strong enough to keep the thermals down. You might also find that thermals are popping off in the middle of the valley like this. So you could still find thermals there. Although usually the thermals get sucked onto the rising air on this side of the mountain. And if you fly low in the center of the valley down here, you'll find like a totally different weather pattern usually. Wind is blowing up the valley or down the valley. Oops, I cleared my drawing. Up the valley or down the valley. And in something as big as the Owens Valley, it's just, you kind of keep that in mind, and I would rather pick like probably the sunny side to get the free lift, and you just like fly your course. But if you're somewhere that's much tighter, let's say Yosemite Valley. Where's Yosemite Valley? Whatever, this valley will work. Let's say you're flying in the gnarly mountains, and the sun is on this side, heats up this cliff face here, air is going up this way, and you'll find the cloud here. It's flowing down here, and then you have the valley wind going really fast one way or the other. It's kind of usually what's happening. And at this point where they meet, it can be a washing machine. Especially like when you punch down through it. It can be a real washing machine. So if I was flying in the gnarly mountains in the middle of the day, I would stay pretty high out of the gulch, out of the ravine part. Unless I was brave, you could venture down and see what it's like, but, don't be surprised if you encounter something totally different down there. One way to think about this is this shaded side of the slope is like shedding all this cold air, and it flows down just like the water. It's another way to think about it. So, yeah, you'll get that tailwind going downhill. So, it'll make for a nasty landing if you had to like bomb out down here. You're going downhill with the wind, so you're gonna have a fast landing. Anyway, yeah. Free flyers will stick to the sunny side. And yeah, you'll find the clouds on this side of it. Make sense?
Yeah.
Alright, let's see, sun position. Should I do... You want to talk about coastal patterns now, or should I go into some examples of like some routes I've flown and weather stuff I've encountered?
You guys can.
Do you guys fly the coast a lot?
I will.
We got one.
One? Sounds like indecision. Should I...
I want to see your routes at some point, but maybe we should talk about the coast stuff first, because that's like a whole other module.
Alright, alright, I'll do the coast, I'll just make it really fast. Because, we do fly the coast a bit. I'm gonna go back to this familiar coast. Whoa. The earth is like tilted. Alright, is it caught up? Are we there?
Still traversing.
They're 12
Briefing
seconds
it.
behind right now.
Humboldt Bay.
You see it? Alright. Okay, so some stuff you may encounter when you're flying at the coast. Especially West Coast is mostly what I'm talking about, because a lot of the West Coast is kind of the same as far as weather patterns, and it's very different than from the East Coast. So this is mostly West Coast that I'm talking about. Okay, let's see. Here's an effect that we experience a lot, and this is called thermal blocking or thermal shielding. And it will look like this. Sun heats up the inland area, and you get like that warm pocket of air. Cold marine layer is over here on the left, and it's pushing inland. But winds aloft, it's being pushed inland by the winds aloft up here. And cold and warm air don't like to mix, and sometimes the land will try to really hold on to its warm air. It's like it's sticky. You kind of think of like surface tension. That's not really actually what it is, but like visual aid. Think of it like it's sticky, right? It's sticking to the land, and the cold air will sort of hit it and slide up over top. This would be yeah.
Why does it sometimes slide underneath, and why does it sometimes go over top? What's the difference?
It can do both for different reasons. Lots of weird. There's like every combination of air you can think of can happen. What you want to do is look at the forecast. You want to look at the sounding. That'll pretty much show you which layer is on top. And then when you get there, you want to be looking at the clues to see and like interpret yourself what is going on. So I can kind of share like what the clues would be that this is happening. Alright, so in this case, if the cold air is blowing over top, you will find clouds. Well, you'll usually find like fog going like this and lifting as it goes up and over like this. And there will generally be nil wind at the LZ on the coast. No wind, usually. Even though the forecast says that there's going to be, say, 10-mile-per-hour wind up here, and you're experiencing nothing. It's usually because this warm pillow of air is sort of protecting you, and this cold air is sliding over top. The cold air sliding over top is usually only possible when the difference in temperature is pretty mild, so this isn't like a crazy condition. It's just you notice it more in the wind speed, where the wind is nil, but it shouldn't be, shouldn't be nil. The only thing well, there's two things I would think about in this flying in this situation. The first is that there may be a shear layer right here, where the two layers meet. Depending on like how fast the wind up top is moving, it could be really rotary or it could be really smooth. So there could be shear there. The other thing is the wind could suddenly pick up, because if the cold air gets a little bit colder and it pries its way under the warm air and like a wedge pushes it back, and the warm air gets driven back, the situation you end up with really quickly looks like this. Cold air and fog. Dense fog pushing in with the clear warm air up top. So you have this inversion layer. And what you'll experience is that the wind suddenly picks up and you suddenly get a ton of ground fog. In fact, I've been flying here before where we flew. There was some cloud out here. The weather was great. It was pretty low wind, kind of warm. And we flew from here. We went down the coast. We got inland. We looked at some cool stuff, and we started heading back. And by the time we headed back, the cold air had slid underneath, picked up that warm air, and as the warm air picked up, it quickly condensed into super thick fog, and the whole bay fogged in really suddenly. Like within a few minutes, the whole bay was just like solid fog, which was really fun for landing at the LZ through all the fog. Yeah, those are the two situations that can happen when the cold air is blowing over top of the warm air. Let's see. Any questions about that? Does it make sense?
Yep.
All right.
Yeah.
Let's see. Another one that's slightly less interesting, probably, but it's kind of good to know. If the winds are forecast to be blowing like this, oftentimes on the shore you experience them coming much more perpendicular, like this. And that's because of friction. The high winds coming towards the shore hit the obstacle of the land and slow down, and it's like a diffracting effect where the wind will curve inland like this, generally along the ground anyway, which is kind of nice. So you don't always have to, if you were like ridge storing, you don't always have to be afraid that like the wind is coming at a steep angle. Sometimes it's actually not as steep as you think it would be. Alright, let's see. Anything else to talk about coastal weather? What I just talked about was blocking, heaving. That's like when the cold air slides underneath and suddenly picks up all of that warm air and it condenses really fast. Microbursts. These can be really dangerous. So we probably know about microbursts inland where, like, say there's a gust front, you know, like a cloud collapses really quickly and just like shoots out all this wind. Near the coast, it can be a bit different and weird. Because we have these two things generally fighting each other, where you have the warm on the land and you have the cold over here, they can mix really funny. Like, the diagrams I'm showing will show like one over top of the other, but they can also like go like this, where there's an inversion layer up top and a cold air like slivering in right in the middle, and then it's warm air down on the ground. They can do weird things like that. And the boundary layer between the two layers can also move back and forth really quickly. So let's say there's a low pressure warm air out here blowing in, and it's kind of cool in the morning, and you got all this air out here over the land. It's kind of cooler, and you got this warm air of the low pressure zone blowing in, and it's like holding back this cold air, and it's meeting it at the shore, and it's like kind of stagnant, staying there. But very suddenly the cold air can like break free and slide underneath the warm air as it lifts up. And this would cause, like right along the ground, could cause a dramatic burst of air pushing you out to sea, which could be pretty scary. This would be a microburst. One clue that this might happen is if, well, you know there's a low pressure zone coming in, and if you see clouds, you know that the air coming in is kind of warm, and if you suddenly see like a ton of clouds forming right here, and they're kind of slanting up as they get closer to the shore, that means that air that's in here could be sliding underneath it, pushing up this warm air, causing it to condense and form clouds. So that could be a sign of like very sudden offshore winds. Alright, I think I covered everything. So, in coastal patterns, anything else you guys want to talk about with coastal stuff before I just go on to something else entirely?
Clear.
What was that? I couldn't really hear.
We're all good.
Alright.
Just amazed at your drawing ability.
You like my drawing?
Yeah, they're fantastic.
Great. I'm glad they're legible. Alright. Okay, so next section. This will just be like a series of miscellaneous cross-country flights and different weather things that I've encountered. And I guess what I want to give you is sort of like examples of how you should be looking at your route that you're planning when you're going cross-country, and thinking about not just like, oh, it's great and flyable where I'm taking off from, but like, where am I going? What am I going to encounter? Like, what are the actors at play? Sort of hazards am I going to encounter, and then how should I plan my route, right? Because sometimes the longer way around is going to be a lot better than the direct route. Alright, so this first example, this was the first flight of the Wingman trip. I'm facing south, looking at Mono Lake. Let me know when we've caught up the video feed.
This looks familiar.
Is this bringing back like some PTSD for anyone?
Oh yeah.
I appreciate the wingman references throughout this, though. It's pretty rad to look back at it.
Yeah. That's nuts. Alright, don't be offended if I say that certain routes that certain people took was not a good idea.
No, I wish I flew with you. You know what's going on.
Alright, okay, so, first flight of the wingman trip. Let's talk about the big things that were going on. Is this going to be confusing? I'm facing south right now. Hope that's not confusing. It's the direction I'm going to go. Okay, I'll just use more visual aid. We're taking off from here, and we're flying this way. The Sierras are right here. And that whole week, there was a big-ass low-pressure zone right here. Huge storm. And low pressure left, so the winds were going this way. And they were shooting over the top of the Sierras, like howling over the Sierras. Right over the tops, it was like, I think it was like 30 gust 60 or something. It was nuts. Super high winds coming over the Sierras. Bringing some rain, but I think most of the rain just kind of like dumped on the Sierras, and then we didn't really get rained on. But anyway, that's the big picture of what was going on. So we knew it was going to be nuts when we were taking off. And then here is what we wanted to do. Our LZ was right here. This is where we're taking off from, and we wanted to go down the valley over here, the top of the screen. In the middle, there was a very tempting Lee Vining right here for a fuel stop / camping. Very tempting because it's the perfect distance, and it's along the road, and it had a runway, but it came with some certain hazards because the wind was coming like this right over the top of the mountain tops, which caused unbelievable rotor like this right on the other side of this mountain, and this is right where Lee Vining is. There's the runway right there.
Oh, you're way behind.
Yeah.
Oh,
Okay, just zoomed in. Then.
You see it?
We can maybe use another screen recording to start.
wind's going this way. It's very tempting to go
Oh, there's the
this
runway.
way.
Are we caught up? I zoomed back out.
Yeah, we're now zoomed back out. Oh, now we're at 80,000 feet.
Great. Okay.
Might help to do another restart on the screen sharing.
Alright, I'll do that.
Caleb in the cloud was diamond.
Alright, should be sharing soon. Alright. So, when I was planning my route, I knew that I did not want to go anywhere right on the right side, just up against these mountains, because it was going to be a total washing machine, which people who did fly that direction experienced that. In fact, I think it was like 4 pilots in the first flight tried to go to Lee Vining, and all of them landed before they reached it. So, pretty experienced pilots who know what they're doing, so it gives you an idea. It was pretty gnarly. Anyway, I picked a route that went this way. I still didn't make it all the way. Well, I guess I kind of did, because we planned to camp here, right here, but we weren't even able to launch in the next morning, really. We didn't get very far. But anyway, this route, something that we encountered that I did not expect, because I don't have a ton of experience flying in like terrain that's this big, is, let me get a good view. That's not a good view. Let me spin the other way. Alright, I've positioned the camera. Let me know when it's caught up.
That looks right.
4,
Facing the mountains.
2. Okay. Alright, down here at our LZ where we started on the left side of the screen is 6,200 feet. And there's a, this is going to be really hard to see, but there's actually like a slope here. Drops back down to the water. And at the peak, this is, I think I remember correctly, it was like 8,400 feet. So it's actually like essentially 2,000 feet climb over something that like looked tiny next to the mountains. So as we started flying, we weren't that high. We were like, I don't know, 500 to 1,000 feet, high enough for reserve, but not crazy high because we had that super high winds howling over our heads. We didn't want to go up into that because we were kind of flying into it, headwind. So we stayed kind of low, and we plotted this course, and we're flying up the hill. However, the winds were coming, we were going straight into a 15 mile per hour headwind, flying uphill. So the wind is racing over this little peak and down into Bridgeport Valley at like 15. So what I did not expect was how strong that sink effect can be when you're flying uphill into that wind. I remember testing it and experiencing something like 400 feet a minute. So 400 feet a minute sink effect. My full power climb without any camping gear at sea level is like 800 to 900 feet a minute climb. With camping gear, it goes down to about 600 or 700, and then at this altitude, my full climb is barely over 400. It's like maybe 500 feet a minute best at this altitude. So I was trying to fly up this hill where the wind is going down so fast that it's like the rate that it's going down is 400 feet a minute. My maximum climb is about 500 feet a minute, maybe. And the slope is such that to even stay at the same AGL altitude, I would need like I don't know, 200 or 300 feet a minute, something like that, maybe. Maybe not quite that much, 150. But I didn't even have that, and so I found that I was basically flying straight into the side of this hill. And myself and also my wingman, we had to like turn back downwind and circle to gain altitude to push forward and get over this crest. Once we got on the other side of this little peak, there was a pretty good ridge lift over here. Like, it was really floaty. It barely sank at all coming down over on the other side with the water. But that was pretty interesting, and it was kind of scary. I mean, aside from being like the first flight of the trip, and being in like severe turbulence, the fact that like I'm full throttle, like pegging it, and I'm a light guy, so I'm used to just like shooting like a rocket, and I'm just like flying level straight towards the ground. That was interesting. I pretty quickly figured out what was going on. But this is a factor to consider. If you're planning your route, you know you're going into a headwind, think about the terrain. What is the topology doing? Am I flying up a gradual gradient, or am I going down a gradual gradient, or is it level? if you're going up a gradual gradient, you need to think very carefully about your fuel endurance, because you could be full throttle, which is going to be like 8 liters an hour on a Moster-ish. You could be pegging it and not even climbing, and you have to like turn back and circle just to climb, which can make this route with this, you know, a 15 mile per hour headwind is like a very inconvenient wind under normal circumstances. It's not like, oh, I can't do anything, you know, but it makes this route questionable, right? So, yeah, that was interesting. Any comments on this situation? Anybody ever felt this?
I was there with you and experienced that, but I didn't know what was going on. I knew there was a slope, but I ran into that exact same thing of, wow, I'm at full throttle going basically down into the side of this mountain. But I didn't understand the why of the sink on the backside. So thank you for explaining that. That's right.
Nice. Yeah. Good times.
Great times.
Good times. Alright. Yeah. So, talked about lee side turbulence. Talked about this downslope wind can be extremely formidable. Let's see what else to talk about this situation. Here's an interesting data point. So, let me measure this distance real quick. The far side of the lake to the mountains, 15 miles. Okay. Here's an interesting data point. So, from here to here is 15 miles. "15 miles, so you'd think that'd be enough to get rid of all of the lee side turbulence." It was not. So the wind was going over the tops at, like, again, it was like 30, gust 60. It was insane winds. I never would have flown if it wasn't for, like, you know, the pressure of the adventure wingman thing. And we were flying. I got over this crest. Let me pick a different color here. I got over this crest and turned this way. Went around this side of the lake. And there's basically 10 miles in front of me of, like, totally flat. There's nothing there. And it was still, like, insanely rotary. Like, taking tip collapses, but mostly just getting, like, heaved up and down. Like, insanely. He just like, you can feel it just, like, pulling you way up and then dumping way down. But it's not thermals, because right in front of me is this huge body of water. And it was, like, in the morning, the sun is barely up. It's not thermals. It's rotor. It was nuts. I guess the takeaway there is the principle of how far rotor goes. The faster the wind, the exponentially farther the rotor will propagate. It's not linear. So if it's 20 miles per hour going over these peaks, say the rotor will reach here before it becomes, you know, manageable. If it's a little bit more, 25 miles per hour, it could be here, twice the distance. Another 5 miles per hour, it could be way out here. So that was 20, 25, 30 could be way out here. Just like the rotor just never stops. It's just everything is churned up like a washing machine. So that's something to think about when you get into, like, high winds. High winds are happening. Be very careful about, like, thinking, oh, the winds are over there, you know, it's no problem. Because the stuff can propagate pretty far sometimes when it's high winds. The next morning when I took off, let's see, get a good vantage point. 66 and 82. Okay, The next morning, we took off from around the lake bed, where it's 6,600 feet. And the top of this little peak right here was 8,000. Which, when we're flying, looks really small compared to the Sierras on the other side, which are just huge, right? Some of these things are topping off at like, well, way down here it's like 17, but I think over here it's almost like 10 or 12? I can't quite remember. 12,000 feet? So, we took off from here, and we wanted to fly this way and go over into Mammoth Lakes. And the wind was blowing still over the Sierras this way at, you know, breakneck speeds. And this little hill did not look consequential. I mean, I say little, but it's, you know, like 1,500 feet. Did not look consequential. But it totally was. We got close to this thing, and we started encountering turbulence, and we were going to bug out from Mammoth Lakes and keep going around the lake and land at a little parking lot that was like right here. But when we got behind this hill, there was one point where, again, this is in the morning, there's no sun yet, there's no thermals, but I was motor off, and my instrument said I was doing 1,000 feet a minute up in rotor. And I happen to know, with all my gear in that configuration, at that altitude, my sync should have been about 17, sorry, not 17, should have been about 700 feet a minute, throttle off, with all that gear at that altitude. Just sync pretty quickly in that wing. 700? Maybe closer to 600 feet a minute. So, but I was going up at 1,000, which means that, like, the wind in that rotor was about 1,600 feet a minute going up. It's like crazy, crazy rotor. It was like right after that, like all three of us kind of over the radar were like, I'm landing, okay. we just like landed right where we were. Anyway, so that was fun. That was the morning, I think. The other guys out of Bridgeport were going to Lee Vining. That was the morning that Chuck experienced like 25 miles per hour on the ground over here by Lee Vining. I think that was when. Yeah, because we picked him up. Anyway.
Just
Yeah,
for
he landed in the airport.
quick context, 1,600 feet per minute is 20 miles an hour.
Yeah.
Ridiculous amount of air going straight up.
Ridiculous. When, so Owens Valley is famous for free flyers, both, well, actually mostly hang gliders. It's actually world famous. It's a world-class site because in the summer it gets these gigantic thermals. They're really big across and they go really fast, which is great for hang gliders because they have a bigger turn radius. Anyway, they get so powerful in the summer and peak time that like hang gliders can get like flipped over upside down. And they say those, like the really, really big ones, can top out at close to 2,000 feet a minute. So essentially what I was feeling was like one of the biggest thermals ever. But not a thermal rotor, which is probably worse. Just for some context on the numbers. Alright, I think I've beaten this example to death. Lee side sync, coming up to the mountain. Avoid the rotor at Lee Vining. Rotor behind the foothills. Next example. Let's zoom over to St. George. St. George, St. George. Alright, our route was taking us... Alright, is the video caught up? We're looking at St. George?
Nope.
No?
Getting there.
Are we there?
There, yeah. And I see the Virgin Gorge.
Yep. Alright, so St. George is a very interesting area. This is another great example of like understanding the topology that you're traveling into and knowing what the common actors and like effects are in this area. Multiple local pilots warned us about this this thing that I'm going to show you. I don't know if I probably wouldn't have thought about this too much. Like I wouldn't have thought it would be this strong of an effect if the local pilots hadn't warned us. So anyway, talk to local pilots where you're going. But if not, think real carefully about your route. So anyway, this is St. George, and it has mountains surrounding it, like so. It's kind of like this bay area without the water. It's like a bowl. And at night, it fills up with cool, dense air, and in the morning, all of that dense air spills out through this gap right here, the Virgin River Gorge. It's a familiar story, right?
Oh yeah.
Yeah. Local pilots warned us that airplanes will... well, the Virgin River Gorge is like really beautiful and it's like really crazy if you've ever driven through there. Local pilot warned us that airplanes will sometimes crash in this gorge because they get surprised by how strong the wind is. The drainage effect can be. So if it can flip an airplane over into a gorge, then I don't want to be flying through that on my bed sheet. So anyway, here's a closer view of the gorge when you guys catch up. My route, I was taking off from Mesquite in the valley, and I needed to land in St. George. So I have to go through here somewhere. So what I ended up deciding to do was, on the right side, we got this mountain, a hazard area, at the gorge and at the bottom of the gorge, because the air is going to spill out into the valley. My route was to essentially go really high and go around to the right side. And it was totally smooth because you dodge all of that drainage coming out in the morning. But if you don't know this, then you might come up to this gorge and it looks amazing and you're like flying towards it. It's like, oh, this is awesome. And then like you experience like gnarly stuff. It's all draining out through that inlet. It's kind of like flying through a valley where you're flying up against one of the rock faces on one side, or like the sunny side. In this case, it's not the sunny side, but like I was going around it, essentially. Does that make sense? I can't like see anybody nodding or anything if you guys are.
It's nodding.
Okay.
Caleb, I sent you a text.
You sent me a text?
Yes.
So who got the touchdown?
Alright. Let me see if I had anything like really interesting to talk about left. We talked about this. I had an example with Bora winds in Iceland, but we don't really need to talk about that one. It's actually not that interesting. I think that mostly wraps things up. So I covered a bunch of fundamentals, gave a bunch of examples of like mostly just trying to instill the idea that, you know, it pays to think about the topology and think about the bigger picture, weather effects, what's going on, so that you can know what to expect, and then when you get there you understand like how stuff mechanically works with the air, so that you can interpret like what's happening. I think that's everything. Like, subscribe, ring the bell to get updates.
Thanks, Caleb.
Caleb, I have a question on when Jean-Francois did his trip. He took the methodology that if he just went to 10,000 feet and every single leg that he did higher, he was gonna less likely to have to deal with all these things. So as long as he knew where he was gonna land and the forecasting for that and where he launched, then he didn't have to get into everything cross country. Is there an altitude of AGL where suddenly things do change, or is it?
I wouldn't say there's like a particular altitude, it just sort of slowly bleeds off, right? All these effects. If you're going to do all your cross country at 10,000 feet, mostly all you have to worry about are jets and headwinds, right? Because if you go up 10,000 feet, maybe, or higher, maybe you encounter like 20 or 30 mile per hour headwinds, so you just don't go anywhere. So that's what you'd think about. Also, it's an interesting mentality. I think it comes with some hidden danger because you get to your destination and now you have to descend, and so you've kind of put yourself into a situation where you have to do something instead of like approaching the area and having the option to go back. I don't know. Could be.
Yeah, he had that. He definitely had that problem a couple of times.
Yeah, so that comes with its own downside, I think.
Anyone's got any questions?
This is great. Thank you so much, Kate.
Have you done any college teaching? Because you're pretty dang good at this.
Thanks. No, I haven't. I do like explaining things, though.
Yeah, we need to get you to come here and do a class and with some equipment on comms as well, because we're still facing the same issues.
On
We always
comms?
do. Yeah.
Oh. Alright.
Oh. I can't quite hear you. No, but what's that? The connection's going bad.
I'm going through a tunnel.
We can see that, Caleb.
Alright. Thank you all. You all been great.
Thank you.
See you guys.
See you tonight.